Hello everyone, this is Rakhi Kaushik and today we'll be doing coordination compounds part 2. So in last class, we discussed what are coordination compound, the importance of coordination compound. I told you about how they look like. So we have a central metal which is mainly a transition element and ligands are joined through it by a coordination or a dative bond. And I told you different terms like this is the central metal, these are the different ligands, and they are put in a bracket that is called as coordination sphere. The species inside the coordination sphere are non-ionizable. We also call it as a secondary valency according to Werner's theory. And the one that are outside the bracket, they are ionizable ions. They are called as primary valencies. And we studied the difference between coordination compound and double salt. I told you that whenever we put in water or we dissolve it, the coordination compound, they split up as the ions outside the bracket, that is ionizable, but the one which are inside the bracket, that is the coordination entity, they do not ionize. So they ionize as a single unit. While in double salt, they dissociate into simple ions when we dissolve in water. And after that, we studied the different terms used, like the coordination complex or the ion. It can be cationic or anionic depending upon the charge on it. If you find a positive charge here, it means it's a cationic entity. And if you find a negative charge here, like this one, we call it as a anionic complex or anionic entity. Then we have a central atom, which is mainly a transition element or an inner transition element, which is joined to different ligands by a coordinate bond. Now, what are ligands? Ligands are the electron donating species. They can be ions or they can be normal molecules. Now, ligands can be of different type. They can be a unidentate ligand, which has one donor site. Uni means one. So the one which has a one donor site, they are called as unidentate, like water or ammonia. So oxygen, water, it binds through oxygen because oxygen has lone pair of electron. Ammonia also, nitrogen of ammonia has a lone pair of electrons, so it bound by that. So it's a unidentate. It can be bi or didentate when we have a two donor sites. So you can see oxalate ion, which we represent as a short form as OX. So it can have it has two donating sides, this negative and this negative. Even ethylene diamine, if you see, it has two donating side, the lone pair of this nitrogen and the lone pair of this nitrogen. So this is also called as symmetrical bidentate ligand because it is symmetrical in nature. Then we can have an unsymmetrical bidentate ligand like this glycinate ion. Can you see it is unsymmetrical because one side it is donating through lone pair of nitrogen and other side it is donating through the negative charge. Now the one which has more than two donating side, they are called as polydentate ligand. Poly means many and dentate is the donating site. So example is EDTA. Now EDTA, if you see, ethylene diamine tetraacetic acid. So you can see tetraacetic acid. Tetra means four. So four acetic acids are there. So it has a four donating side, these four negative charge through which it can donate its lone pair and it can make a coordinate bond with the central metal. Plus, it also has two sides where nitrogen has a lone pair which can also donate electron to the metal. So in total maximum it can have 4 plus 2, 6 donating sides. So it is also called as hexadentate. It is also called as hexadentate ligand. Now, depending upon the metal, the requirement of a metal, it can donate from 2 sides or 3 sides or 4 sides or 5 sides. So we also call it as a flexidentate because it is flexible in donating the electrons. Then we have a ambidentate ligand. Ambidentate ligands, these are the unidentate ligand, but they can attach from two sides. For example, if you see CN, now it can donate through nitrogen side also or carbon also. So same way NO2. NO2 can donate from nitrogen as well as oxygen. So when it donates from nitrogen, we call it as nitro, and when it donates through oxygen, we call it as nitrito, or maybe nitro N, nitro O, like that. Same way SCN also can donate through sulfur or nitrogen side. So this thiocyanide also is a ambidentate ligand. Then we have a chelating ligand. Now whenever a polydentate ligand, when it attaches from more than two site or more than two site, it makes a ring-like structure or a cyclic structure. Can you see it's a cyclic structure here? So that's why we call it as a chelating ligand. For example, if I write this as NH2, CH2, CH2, NH2. So here nitrogen, it is binding through this nitrogen as well as this nitrogen. And you can see with metal, it is making a cyclic structure. So we call it as a polydentate ligand. So this, if I see ethylene diamine, or we also call it as ethane 1,2-diamine, it can be a polydentate because it has more than two donor site. It has two donor site, actually more than one. It is also chelating because it is making a cyclic structure, and it is symmetrical didentate ligand because it is symmetrical. Okay, then we have, this is the ligand. It's a table of a ligand. You need to learn it thoroughly. If you observe here, you will find that the one with the negative charge, they are ending with O, oxalate, O, sulfate, O, amide, O. The one with the positive charge, they are ending with EM. EM, you can see here, nitronium, nitrosonium, hydrazinium. So the one with the positive charge. And we have a neutral ligand also, which donate through lone pair, like aqua, that is water, amine, that is ammonia, nitrosyl, that is NO. So you have to learn this table. These are the common ligands that we use in coordination compound. Next is the coordination sphere. I told you this thing earlier also, the bracket in which the central metal and the ligand that are attached is called as the coordination sphere. Now the number of ligand that are attached to the central metal is called as coordination number. For example, if I see this metal, I can see 2 ligand and this is another 2 ligand. So total 4 ligands are joined to this metal. So the coordination number will be 4. Clear? Now the geometry or shape of a molecule, because there is a particular spatial arrangement of these ligands around the central metal atom. So they are arranged in a specific way in space around the metal that gives rise to a specific geometry that we call it as coordination polyhedral. Now depending upon the coordination number or the number of ligands attached to it, it can be linear if the coordination number is 2. If coordination number is 4, it can be tetrahedral or square planar. And if coordination number is 6, it can be octahedral. So these are the different shapes or geometry we get depending upon the coordination number. So if coordination number is 5, it can be trigonal bipyramidal or it can be square pyramid. This we have done in the chemical bonding chapter also, the different geometry as well as the hybridization also. So it can be cis when they are on the same side, the ligands, similar ligands are on the same side, or it can be trans when they are on the opposite side. Okay, so this is a beautiful way, you can three-dimensional view of the coordination compound where we have in center, we have a central metal and the ligands, they are arranged in space with a specific geometry. Now I want you to solve this table. Here you have to tell the coordination number or the coordination entity and the central metal, the coordination number, the ligand and the shape of this particular compound. Okay, so this is NH3 because the ligand is ammonia here. So try to solve it. Once you are done, you can check out the answers. Now we have a homoleptic or heteroleptic complexes. When we have a same type of a ligand, that is called as homoleptic complexes. But in a complex, when we have a different type of a ligand, you can see here one is ammonia and one is Cl. So that we call it as a heteroleptic complex. After that, we discussed the Werner theory, where I told you that Werner, he experimented, he took different cobalt compound and he found that there are two types of valencies, primary valencies and secondary valency. Now, if you see this coordination compound, the one which is outside the bracket, so you can see there are 3 chloride ion, so that represents the primary valency and this valency is ionizable. It means when I put in water, it will ionize, the Cl will go off as 3Cl negative ion. While the one which are inside the bracket, so all the ligands that are present inside the bracket, they represent the secondary valency. So you can see here there 6 ammonia are present. So it means the secondary valency is 6 here. This secondary valency, it is directional, it is fixed, and based on this we get the geometry of the coordination compound. So can you see here I have represented it with a dotted line. The primary valencies I have represented with a dotted line, and the secondary valencies with the dark lines. Then he did different experiments. How he came to know about the primary and secondary valencies? He took a different cobalt compounds and he reacted them with silver nitrate. So you should know that AgNO3, when it combines with Cl negative ions, it gives white PPT of AgCl. And he just found out the number of Cl negative ions released by checking out the conductivity by doing electrolysis. So he found the number of electrolytes. So based on that, he found the structure, that is primary and secondary valencies. For example, if you see the first compound, like here. Now, the first compound, he found that total 4 ions were there in a formula unit. So 3 Cl negative ions per formula unit were free. So 3, AgNO3 combined to make 3 AgCl. Now, 3 chloride were free, so it means the 3 chlorides were outside the bracket. So the formula became like this, where all the chlorine are outside the bracket. But when it was purple, he found 2 chloride are free. So it means only 2 chlorine were outside the bracket and 1 was inside. So this way he found different color and could be able to make primary and secondary valency. Now suppose in case of, here it is chloride, if it is sulfate, then the test that we do to detect the ion is we add barium chloride, and if we get a white PPT of barium sulfate, this proves that sulfate is outside the bracket. After this, we discuss the oxidation number. So the way we have done in the redox reaction, same thing we do here. So this is, suppose this is the example. Suppose if I have to calculate oxidation number of cobalt, so I'll take it as X. Now you need to know that ethylene diamine is a neutral ligand. So its oxidation number is 0, and there are 2 ethylene diamines, so we'll multiply by 2, plus the chloride ion oxidation number is -1, NO2 is also -1, and you can't see any charge outside the bracket, so it is equal to 0. Now you just calculate and you will get that oxidation number of cobalt is +2. Okay, similar way you can calculate for this one also, like FeCN6. So Fe I have to calculate, I'll take it as X. Now Cn is -1. There is a table, you have to learn that table. I showed it to you earlier also, the ligand with the charges. So Cn is -1 and there are 6 Cn. So 6 multiplied by -1 equal to the charge on the ion complex. You can see -4, so you will write equal to -4. And now when you will calculate, you will find it as +2. Remember, this is metal, so you will always get in plus. Just try to do these 3. Try to find out the oxidation number of iron and nickel here. Nickel you will find it as 0 because CO is 0. So 0 multiplied by 4 is X plus 4 multiplied by 0 is equal to 0. So nickel will come as 0. Here C2O4 is a bidentate ligand. So 2 multiplied by 3. So it will be X plus 2 minus 2 multiplied by 3 is equal to -3. And for the first one, it will be X plus 6 multiplied by -1 is equal to -4. Or maybe you can write it as X plus -1 into 6 plus 4 is equal to 0. Then we did this IUPAC nomenclature. So I told you that first we named it cation, then we named anion. Now ligands we write in alphabetical order. If we have more than one ligand, or then we write di, tri, tetra. If we have a complex ligand, then we write bis, tris, tetrakis, like that way. And if the complex is anionic, or we have 2 metals, then we write 8 at the end of the central metal. So we write 8. Cobaltate, ferrate, zincate, like that. Now ligands, just now I told you that whenever it's a negative ligand, it ends with O. Whenever it's a positive ligand, it ends with EM. And the neutral ligands, they have their normal names, like water is named as aqua, ammonia is named as amine, CO as carbonyl, NO as nitrosyl. And after this, the metal, central metal, we write the oxidation number of the central metal in Roman numeral. And we write the whole name as one word. We don't put gaps in between. And if it's a bridging ligand, we write mu at the end of the just bridging ligand. And when it's an embedent ligand, we just tell the attaching site. For example, this one, if you see here, it's a bridging ligand, so we'll write it as bis because ethylene diamine is a complex. You can see En, ethylene diamine is a complex. If I want to write it as diene, diethylene diamine, then it becomes a different ligand. So we will get confused whether we are talking about En or we are talking about dien. So to avoid that confusion, we write bis. Bis means two. So bis ethylene diamine, or we also write it, we can write it as ethane 1,2-diene. So that's the same thing. Cobalt. Now here we'll write cobalt, the oxidation of cobalt, that is 3. And then we'll write it as mu. Now this mu tells that it's a bridging ligand. So mu imido, mu hydroxo. Then again bis, ethylene diamine, cobalt, and its oxidation number. Okay, don't worry, this is the most complex name that you will get. Otherwise, generally we get the simple one only. And if you say we have this embedent ligand like NO2 or SCN or CN, then we tell the attaching site also. For example, this one we have a NO2, so we'll write it as hexa nitro N. Now this N tells that the point of linkage is nitrogen, not oxygen. So hexa nitro N cobaltate. Now can you see here 8 I'm writing cobalt, I'm not writing cobalt, it is cobaltate 8 because it's a anionic complex. You can see a negative charge here. So cobaltate, oxidation number of cobalt, and since it's an ion, so we'll write ion. So it needs practice, and yes, you will get a question from IUPAC nomenclature of coordinate compound. And the simple way is we name it positive first, then negative first. We write ligands in alphabetical order, then we write central metal, then we write its oxidation number. If the anion, it is a anionic complex, then with central metal we write 8 at end. That's the thing we keep in mind. For example, let's see this compound, or let's take another one, this one. Now, if you see this compound, we have a multiple ligands. So we will use alphabetical order. So it is amine and aqua, AMAQ. AM comes before AQ. So triamine, triaqua, chromium 3 chloride. Clear? Because it's a cationic complex, so we just wrote chromium. Now, if you see this one, here we have a complex ligand. So we will write tris rather than tri. Tris, ethane 1,2-diamine or ethylene diamine, cobalt, its oxidation number, that is 3, and sulfate. Now, same way, if you see here, this has 2 metal ion. So we'll write diamine silver 1, that is its oxidation number, and then dicyano or cyanido, depending upon what's mentioned in your NCERT. So dicyanido argentate, and its oxidation number. Now again we can see this complex where we have a 2 metals, you can see here, or we have a negative charge on anion. So we'll start with potassium because we start with positive first. So potassium hexacyanoferrate. Why we write 8? Because there are 2 metals, or this is an anionic complex. So here it will be -4 if I don't want to write this potassium. Clear? So potassium hexacyano or cyanidoferrate, and oxidation number of iron, that is 2. So this is how we write or how we name coordination compound. Let's do more practice. Okay, try to name these compounds. Na2PtCN4 K3FeC2O43.3H2O, CONH35Cl Cl2, FeOH H2O5 Cl2, CrEn3 Br3, NH4 PtCl3 NH3. Let me expand it. Just try to name these compounds. So once you're done, you can check the answer. Sodium tetracyanoplatinate 2. This is potassium trioxalatoferrate 3. This one is penta amino chlorido cobalt 3 chloride. This one is penta aqua hydroxo iron 3 chloride. This one is tris ethylene diamine, or you can also write ethane 1,2 diamine, chromium 3 bromide. This one is ammonium amino trichlorido platinate 2. Now write the structure of or the formula of these coordination compounds. So you can check out answers here. Now it's very easy. If you see, this is hexa, aqua, nickel. The oxidation number of nickel is 2. So that's why there are 2 sulfate here. Okay. So that's why, because sulfate is also -2 and nickel is +2. So charge on the complex is +2. So that's why 1 sulfate is there. Now this is also easy. Hexa, you can see sodium tetrachlorocuprate. Clear? So since the copper is +2 here. Now if you see this one, hexaamine chromium. Now here the oxidation number of chromium is +3. Okay, so it means the charge on this also is +3. Now if the charge is +3, then NO2 is -1. So crisscross method, you remember we did in smaller classes how to write a chemical formula. So 3 will go here and 1 will go here. So that's why there are 3 NO3. Now same way here, Cl is -1, so there are 4 Cl, so -4. Copper is 2, so overall charge is -2 here. So that's the reason each sodium is +1, so that's the reason 2 Na are written here. Okay, so just check out the oxidation number. That will help you to decide how many ions will be there outside the bracket. That is the primary valency. Otherwise, it's very easy. Check out these. If you find any problem, we'll discuss it. Now the next topic is isomers. Now isomers, we know that when 2 or more compounds, when they have the same chemical formula but different arrangement, is called as isomers, and the phenomena is called as isomerism. So the way we did in organic chemistry, these compounds also show isomerism. It can be a structure isomerism or it can be stereoisomerism. Now there's a confusion. Right now the isomerism is deleted from your course, but still to be on safer side, I'm just giving you an idea about the structure isomerism. Okay. Now as the name specifies structural, it means there is a difference in structure of coordination compound. And when we say stereoisomerism, it means there is a difference in spatial arrangement or orientation of ligands around the metal. This stereoisomers can be geometrical, that is cis and trans, or it can be optical isomerism. So we'll not discuss this, we'll discuss only the structure isomerism, that also very quickly. Now structure isomerism can be ionization, hydration, linkage and coordination isomers. Let's see, it's very easy. Now if we see the linkage isomerism, as the name specifies linkage. So if you find any ambident nucleophile, so you'll come to know that there are different points of linkage. For example, NO2 or CN or SCN. So you can see here, these both compounds, they have the same molecular formula. The only difference is that at one place it is NO2 and other place it is ONO. Isn't it? So at one place it is linked by N and other place it is linked by O. That's why it is called as linkage isomerism. Okay. Now second is coordination isomers. Now in coordination isomers, there is an interchange of ligand between cationic and anionic complex. So you will see 2 complexes here. What you have to do, just interchange the ligands. So with chromium, put CN. With cobalt, put ammonia. This is cobalt, not carbon monoxide. Okay, so this O is small one. So you just interchange the ligand in the different cationic and anionic complex, you will get the coordination isomerism. Next is ionization isomerism. In ionization isomers, you will find different ions outside the bracket. So you can see here they both have the same molecular formula. Only the difference is here sulfate is inside and bromine is outside, while here bromine is inside and sulfate is outside. Remember, we don't change the coordination number. So here it is 6 coordination number, 5 plus 1. Here also it is 6, 5 plus 1, 6. So if I'm moving something outside, I have to move something inside also. So, and we can do a test also to see that this is an ionization isomer. If I put barium chloride to it, I'll get a white PPT of barium sulfate here, showing that sulfate is present. We'll get a white PPT, while in this one we'll not get the white PPT, showing that we have a different ions outside the bracket, and the one which is showing white PPT has sulfate. This is a test for sulfate. And if I want to see a test for bromide, we put AgNO3 and we get off-white PPT of AgBr. So this way we can tell different ions were there outside the bracket, because you know the primary valencies are only ionizable. Next is the solvent isomers. That's very easy. You can see here the number of water molecules are different inside and outside the bracket. Again, remember, we don't change the coordination number inside. If it is 6, so there has to be 6 ligand to it. So you can see 6 water here, 3 Cl outside. Now you put just 2 water outside, so you'll put 2 Cl inside. So you will see 2 water outside. Now you can take out 1 more water and make it as 3 water outside and all the 3 Cl inside. Clear? So this way we also call it as hydrate isomers. Hydra, the water, isn't it? And water is a solvent. So it is also called as solvate isomers. Now the different number of water molecules are there inside and outside the coordination complex. Okay, isn't that easy? So linkage isomers, they have an ambident nucleophile or ambident ligand. Coordination isomers, they have different ligands, you just interchanged. Ionization isomers will have a different ions outside the bracket. And solvate isomers, they have a different water molecule inside and outside the bracket. This is how these compounds look in 3 dimensions. Okay. Now after IUPAC, we'll do bonding in coordinate compound. Now first we studied the Werner theory, where he told about primary and secondary valencies. So he told that primary valency is ionizable and secondary is not, and secondary gives structure or geometry to the coordinate compound. Now before that, please make sure you do all the in-text and back question of this chapter, especially the in-text one. Chances are that you'll get the direct questions from book only. Okay. Now there was some drawback in that theory, because though he was the first one to explain the bonding features in coordinate compound, but his theory couldn't explain some questions like why only certain elements they make coordinate compound. Second thing is that why coordinate compounds are directional, why they have a specific geometry. And third, it did not tell about anything about magnetic or optical properties of the compound. So it means we need to look for some other theory. So different theories were given, like valence bond theory, crystal field theory, ligand field theory, molecular orbital theory. If you remember, you have done molecular MOT, molecular orbital theory, valence bond theory, and Vesper theory in your chemical bonding also. Okay, so we'll discuss here the valence bond theory. Now in this theory, the magnetic property and magnetic moment values of complex are given to predict the hybridization of a compound. So basically we can tell the hybridization of the compound also by this theory. Okay, and we can tell the magnetic property, whether it is diamagnetic or paramagnetic. Now it says that metal, under the influence of ligand, it uses its orbitals like s orbital, p orbital, or d orbital, or n minus d orbital. Okay, and it hybridizes. So when it hybridizes, these hybrid orbitals, they overlap with ligand. These orbitals, they overlap with the ligand and they make a coordinate bond. And we can predict the geometry as well as the magnetic property of the compound also. Now to start with, you need to know if coordination number is 4. We have done this in chemical bonding also. Hybridization can be sp3 or it can be dsp2. When it is sp3, the geometry will be tetrahedral. When it is dsp2, it will be square planar. When coordination number is 6, hybridization can be d2sp3 or it can be sp3d2, depending upon which d orbital it is involving, whether it is involving n minus d orbital or it is involving d orbital, nd orbital. Now, if it is d2sp3, it is octahedral and it's an inner orbital complex. When it is sp3d2, it is outer orbital complex. So because d is using like of the same as n, so it is outer orbital. This d is using as n minus 1d, so it is inner orbital complex. So need to know this table, very simple. We have done it earlier also. Second thing, you need to know what are inner orbital complexes and outer orbital complexes. Now, inner orbital complexes, they involve d orbital of the previous one. Okay, so if you remember, okay, you need to know hybridization. You need to know how to write a configuration also for this one. Okay, so you remember we did S, SP, SP, SDP, SDP, SFDP, SFDP. And in atomic structure in your grade 11th, we did how to write electronic configuration, and we have used it in d block elements also. So when it involves n minus 1d orbital, we call it as the inner orbital complex. When it involves nd orbital, we call it as the outer orbital complex. Whenever it involves inner orbital complex, it is either sp3, d2, again I'm repeating, we have an inner orbital complex, we have an outer orbital complex. Now, inner orbital complex is when we have a strong ligand. When we have a strong ligand. So, strong ligand push the electron, pairing of electron happens. What? Pairing of electrons happen. Don't worry, we'll do it in detail. And we also call it as a low spin ligand. And which are the strong ligand? Where the donor site is carbon or nitrogen. Ligands like CO, Cn negative, NO2 minus, ethylene diamine, pyridine, or ammonia with cobalt or manganese. Okay, so when we have a central metal cobalt or manganese, and then we have a ligand ammonia. So these all are strong ligands, strong field ligand. They make a low spin ligands. They push electron, pairing happens. The hybridization, for example, if coordination number is 4, then hybridization is dsp2 and geometry will be square planar. Now, if we have a weak ligand, also called high spin ligand, they make outer orbital complex. Now they are weak ligand, they'll not do pairing. So ligands like where the donor site is oxygen or halogens, like water, OH negative, F negative, Cl negative, Br negative, or ammonia with some other metal, not cobalt and manganese. Okay, now here they act like a weak ligand, they don't pair. Then hybridization is sp3 and geometry will be tetrahedral. Please write this in your notebook. Now, second thing I want you to know is how to write the electronic configuration. You remember we did in our 11th grade structure of atom chapter, how we write the electronic configuration: 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, 4f14, 5d10, 6p6, 7s2, 5f14, 6d10, 7p6. So you need to know how to write the electronic configuration, and maybe you can use the shortcut like putting helium, neon, argon, krypton, xenon, or radon in between when the atomic number is high, because we are using transition element, so most probably it will be high. So same way, if I have coordination number 6, so it can be inner orbital complex, it can be outer orbital complex. Inner orbital when it's using the inner d orbital, and outer is when it is using the outer one. The hybridization will be so we'll be taking inner orbital complex or outer orbital complex. Inner orbital when we use the inner d orbital, outer orbital complex when we use the outer orbital, outer d orbital. Hybridization will be D2sp3 in inner and sp3d2 in outer, and same thing, that inner will involve strong ligand and outer orbital complex when we have a weak ligand. Now let's start. Let's take example. For example, if we get a compound like this, CONH3 6 3+. Okay, now first we'll write the electronic configuration of cobalt. Now cobalt is Ar18 4s2 3d7. Okay, so we'll write, now it is not cobalt, it is CO plus 3, cobalt plus 3. Okay, so we'll remove 3 electrons, 2 from S and 1 from D. So it will become 3d6. So 3d6, 4s2, 4p. Now 3d, 4s, 4p. 3d6. Now you can see there are 6 ligand. It means we need 6 empty orbital where these ligands can put their lone pair and they can make their coordinate bond. Clear? Okay, fine. So first we'll write the configuration of cobalt plus 3. We'll check out the ligand. We'll come to know how many empty boxes we need. We'll write the configuration with empty also next to the configuration. Now after this, we'll see what type of a ligand is ammonia. So you can see ammonia with cobalt is a strong ligand. Now strong ligand, it means it will push electron and it will make them pair. So it means this will pair with this and this will come here and pair with this. So these all will be paired and we'll have these two empty because these electrons, they are shifted in these orbitals. So we have 2 empty d orbital. So 2 empty d orbital plus 3, third one is 4s, 4, 5, 6. So we got 6 empty orbitals, that is D2sp3. So the hybridization is D2sp3. They will hybridize to make 6 empty orbital and the hybridization will be D2sp3. Why we wrote D2 first? Because D, that of third or subshell, is used up, while this one S and P are of 4. Clear? So we have D2sp3 hybridization. So we got hybridization. Yes. Now what other information we can get? Now we'll see the magnetic nature. Just see the electrons here. If you find any unpaired electron, it will be paramagnetic. That means it is attracted by magnetic field. If all electrons are paired, it means it is diamagnetic, that is repelled by magnetic field. More the number of unpaired electron, more is the paramagnetic nature. Clear? Now here we can see all the electrons are paired. I don't have any unpaired electron. It means it is diamagnetic. So it is diamagnetic. Hybridization is D2sp3 and we can see 6 ammonia molecules making 6 coordinate bond with cobalt and it's an inner orbital or low spin complex and geometry is octahedral. So you can see here D2sp3, it's an inner orbital complex, ligand is strong and it's a low spin or spin paired complex formed. So you can see we got so much of information. We got the magnetic nature, we got the hybridization, we got the geometry, we got what type of complex it will form, whether inner orbital or low spin complex. So these are the information they can ask you by giving you just any example. Are you getting it? So let's take another example, COF63-. Again, number 1, write the electronic configuration of CO plus 3. Okay, so we wrote the electronic configuration. Now see, there is F6, coordination number is 6, so we need 6 empty orbital. So write the next empty orbital also while writing the configuration. So I can see this D is all full, so I'll write 1, 2, 3, 4, 5, 6. So I'll write 4s2, 4p, 6 and 4d, 10 wala empty also, like that way. Okay, now I'll see what type of a ligand this F is. Now this F is a weak ligand. F is a weak ligand. Now weak ligand will not lead to pairing. So it means it will stay as such only. So we will use the next 6 for hybridization. So I'll use 1, 2, 3, 4, 5, 6. So these are the 6 orbital where this fluorine will put its lone pair to make a coordinate bond. Now I'll see which orbital it is using. It is using sp3d. So this sp3d will hybridize. So it means hybridization is sp3d2. Hybridization is sp3d2. Okay. So we got the hybridization, that is sp3d2. Now we'll see the number of unpaired electron. Now I can see 1, 2, 3, 4. 4 unpaired electron in this. So it means it is paramagnetic. And you know, each electron approximately gives a 1.2 Bohr magneton moment. So it is highly paramagnetic because it has 4 unpaired electron. Okay, we got the paramagnetic nature. Then we can see 6 fluorine atom, they are making a coordinate bond with cobalt. And the ligand is weak, so it will make a outer orbital or high spin complex. Also say it as high spin or spin free complex. So just do step by step, write the configuration, see the number of vacant orbital needed, and just whatever the number of vacant orbital you will use, that will be the hybridization. See whether the ligand is weak or strong. So if it's a weak ligand, it will not do pairing. If it's a strong ligand, it will do pairing. And then you check out the number of unpaired electron, that will tell about the paramagnetic nature. If it's all are paired, it is diamagnetic in nature. So this way you got the hybridization, you got the magnetic nature, as well as you got the geometry also. So geometry of this will be octahedral. It will be octahedral. Whenever coordination number is 6, it will be octahedral. Okay, अब आया समझ में? Now try for NiCl4 minus 2. Remember, when here coordination number is 4, so hybridization will be either sp3 or dsp2. And Cl is a weak ligand. All halogens are weak ligand. Yes, so first we'll write the configuration, then we'll see the ligand. Chlorine is a weak ligand, so it will not do pairing. So we'll use the next 4 because coordination number is 4 and we need 4 empty orbitals. So it will use the next 4. So I can see S and P. So 1 S and 3 P will be involved. So hybridization will be sp3. Since hybridization is sp3, so geometry will be tetrahedral. And we can see 2 unpaired electron because it's a weak ligand, so it did not do pairing. So these remain unpaired, and I can see unpaired electron, so it means it is paramagnetic in nature. And this way we got hybridization, we got geometry, we got paramagnetic nature, and since the ligand is weak, so it will be a high spin complex. It's a high spin complex. Now try for this one, NiCN4 minus 2. So here also we'll write the configuration of nickel, that is nickel plus 2 because its oxidation number is plus 2 here. So usually nickel is 4s2. Actually nickel is 4s2 3d8, and since it is nickel plus 2, so I'll remove this s electrons. It will lose 2 electron. So configuration will become 3d8. So I'll write 3d8. I can see coordination number is 4, so I need 4 empty orbitals. So I'll take up the next 4 orbitals which are empty, so that where Cn can put its lone pair of electron and can make a coordinate bond. Now after using this 4, I can see I'm using 4s and 4p. So it will be s and p3, isn't it? Now Cn is a strong ligand, and strong ligand, what they do, they push electron, they do pairing. So this electron will be paired up. So I'll get 1d also here empty. So this will move here. It will get a pairing. I'll get this empty one. 1, 2, 3, 4. So I'll use this 4 orbitals to put electrons of Cn. So since I'm using 1d and s and p, so 3d1, 4s and 4p2. So hybridization will be dsp2, dsp2. And since hybridization is dsp2, so the geometry will be square planar. So we got hybridization, that is dsp2, we got geometry from hybridization, that is square planar. And about the magnetic nature, I can see all the electrons are paired. So it means it is diamagnetic in nature. It is diamagnetic in nature because all electrons are paired. And 4Cn are making coordinate bond by overlapping with these hybrid orbital. So just check out the ligand. Cn is a strong ligand. Strong ligand leads to strong ligand, they do pairing. Okay. So if you know this thing, then it is easy for you to find the hybridization geometry as well as magnetic nature. And since it's a strong ligand, so it will make a low spin complex. Now, valence bond theory, it explains the formation, structure and magnetic behavior of a coordination compound, but it had few shortcomings. Now, first is it made a lot of assumptions. Now, I told you which one are the weak ligand and strong ligand, but nothing has been told in this theory. Okay, so it was very difficult to assume like which one will pair, which one will not pair, and everything depended on that only. Second thing, it does not give the quantitative interpretation of magnetic data, though it is telling that it will be paramagnetic or diamagnetic, but it was not telling how much. Okay, but let me tell you, I told you approximately 1.2 bm per electron. So if anything has 5, suppose a question is there in your NCERT, the spin only magnetic moment of MnBr42 minus is 5.9 bm. Tell the geometry of the complex. Okay, now here the coordination number is 4 and it is tetrahedral. It can be tetrahedral or square planar. But if you see the magnetic moment 5.9, clear? This 5.9 gives an idea that it has 5 unpaired electron. It has 5 unpaired electron. So here it just told about whether it is paramagnetic or diamagnetic, but did not give the quantitative interpretation. Second, it did not tell anything about the color of the compound. Most of the coordination compounds are colored, so it did not tell anything about that. Then make exact prediction regarding tetrahedral or square planar complexes when coordination number is 4. So it was not telling that. Then it did not distinguish between weak and strong ligand. Again, I'm telling you to make or to solve these questions easily. I told you which one is weak and which one is strong ligand, but otherwise when this theory was given, they did not tell anything about weak and strong ligand. Okay, so that's the drawback of this theory. So we gave another theory, that is crystal field theory. We'll be studying in next class. Try to solve these questions by yourself. You have to tell the hybridization and geometry of the following complexes. You can pause the video. Once done, you can check out the answer. I hope this session helped you. Thank you so much for watching and have a nice day.